And this is how we do it. Okay, so we consider passive concentration field, and we call it S. S is the concentration of some pollutant, if you like, within a grid cell. Let's just say it varies between 0 and 1. 1 means 100% concentration, and 0 means 0 concentration. And you can express now the advection of this tracer with the advection equation. This is what's done here at the top. This is the advection. So in the equation you have two sides. On one side, on the left side, tells you how the salinity will change over time. Okay, ds dt. This is the rate of change of the concentration field of S. And on the right hand side is the cause. Okay, and you can see you have two components, and they come from two different directions. You have one advective direction in the x direction, and one comes from the y. What you need to get advection is you need to have a combination of two things. You need to have a flow. Okay, so this is the velocity component here. Can be positive or negative. And you need to have a gradient of your concentration field in that direction. For simplicity, just look at one direction. Just focus on one direction. And essentially what you need to do now in the gridded version of your model, what advection does, it actually passes on the concentration from one grid cell to the next. Okay, so this one is shown here on in this little sketch. This is the most basic advection scheme, is the upstream, also called upwind scheme, but it's highly diffusive. So what you do is you work out that within a time step of how far do you move the content of one grid cell, which is the red grid cell here, into your grid cell, which is the yellow one. How far? Okay, in this example, for example, it is half of the grid cell. Okay, so you move it into half of the grid cell, and because you only have a one value for your grid cell, you have to average this. Okay, you have to average the red and the yellow, and you get orange in the end. And this is the diffusion effect. It's an unwanted effect. It's because of your grid resolution. Okay, and this is what we call upstream scheme. It's called upstream because you have to take into consideration the direction of the flow. Okay, so we only get this advection in this grid cell from the left grid cell because the U component is positive. It actually points towards your grid. Okay. However, you can express it in equations too, which is shown here at the bottom. This one is the formulation and finite differences. Okay, and if you have a look at this equation, it's a linear mixing equation. Okay? And this is a problem because you actually have artificial diffusion. You only get absolutely no diffusion if the time step exactly fits the condition that you pass on the entire content of one grid cell to the next. Okay, and this is what we call the upstream scheme. And I show you a demonstration of the upstream scheme later. All right?